All right, thank you very much. Thank you for having me. Yeah, I'm talking about axioms for the fixed point index of an n-valued map. So if you've been coming to these conferences for a while, you may know I often give talks about axioms in fixed point theory. Actually, I looked back at my records. I've come to 6 of these Nielsen theory conferences. I always have a great time, and it's part of what I like is just being able to see the people every so often. It's a great community that we have. I've talked at 6 of these conferences, and 3 of them have been about axioms, kind of like this talk. This was never my plan, really. I didn't especially want to, but it sort of comes up every few years for me. I also looked, other than me, the number of similar talks about axioms. Anyone want to guess?
No others.
0. So maybe nobody else is interested in this, but I thank you for inviting me back every few years. I think it's interesting. It's good enough for me. I think the topic is especially interesting for the fixed point index. So yesterday, several people mentioned the fixed point index, and today also. And I was paying attention very carefully to what they said about the fixed point index. Gwaski almost gave a definition for the fixed point index. I remember, so I was watching to see if anybody would give the definition of the fixed point index. And at the point in his talk when he first mentioned the index, he said the index, and then he went over to the table and picked up his paper. And I thought, oh, is he going to write the definition? But he didn't. He just picked up the paper. Costa also mentioned the index, but didn't define it. He said something like, the index is kind of a way to count the number of fixed points, something like that, which is a good fake description of the index. We all know it's not quite that. Kate Ponto referred to, she said, we all remember the definition of the index. Maybe we do. So this is something that you probably know if you've been doing this stuff for a while. We almost never actually use the definition of the fixed point index. And if somebody approaches you on the streets of Kortrijk and says, hey, what is the definition? I don't know what to say. For me, I would have to think and evaluate what kind of person I'm talking to and answer in a certain way. Usually, we don't use the definition. We just use some of the basic properties of the index, which is homotopy invariance. There's an additivity property. The relationship of the index to the Lefschetz number. So if I'm talking to someone who knows what the Lefschetz number is, I say, it's like a local version of the Lefschetz number. And they'll say, oh, okay, that's good enough. The idea of essential versus non-essential fixed points, sometimes we'll just say, I think actually this is what John said when he was talking about the index. It's a way to tell the difference between essential and non-essential. So these properties are so good that usually you don't need the definition. You use these properties instead. So instead of a definition, usually, when you read a Nielsen theory paper, they don't give you the definition of the index. Usually they state the properties, and if you want to be really serious about this approach, you can state the properties of the index and then prove that there is only one function that has these properties, and so that's what the index is, and you don't need to give a real definition. You can just say these are the properties, and it's that uniquely determines the index. That's what I mean when I say axioms for the fixed point index. So that's what this talk is going to be about, but in the context of the n-valued fixed point index, which I will not give a definition for. All right, you all know what I'm talking about. Okay, I thought so when I was preparing this talk, I thought, to be honest, I thought the talk maybe was going to be a little short for the 40 minutes time. So I thought I'll just talk about a little bit of history. Theorems of this type really can be traced back to similar theorems about the Euler characteristic. I know of 4 different uniqueness theorems for the Euler characteristic. There are probably others. Some of these are well known. I think some are more obscure. So I thought just for fun, let's talk about some uniqueness theorems for the Euler characteristic. So all of these that I'm going to say are in the category of finite polyhedra, although some of them can be more general than that. all four of them are satisfied in this category, though. So here's the first one. Uniqueness theorem number one. This is Hadwiger's theorem, which is quite a bit more stronger than what I'm saying here. But anyway, if you let epsilon be any real valued homeomorphism invariant of a complex, which satisfies this property, this is called the valuation property. It's kind of an inclusion-exclusion property. So the whatever the value of union is equal to the sum of the two values, and then you subtract the intersection, and the empty set gives you 0. If this holds for all convex subsets of your polyhedron, so they don't have to be simplices, they can just be any subsets inside. And also, this is just like a normalization. If these two properties hold, then your function that you're talking about it must be the Euler characteristic. So this is part of Hadwiger's theorem. Actually, Hadwiger's theorem is much stronger than this. The Euler characteristic is like the dimension 0 case of Hadwiger's theorem, and there are higher dimensional kind of versions of the Euler characteristic, but they are not purely topological. So the higher ones are called the intrinsic volumes of the space, and they are more geometric items, objects is what I want to say. This actually, I became interested in this, and I generalized something like this to the Lefschetz number. You know, the Lefschetz number is similar to the Euler characteristic in a lot of ways, and these kinds of theorems that you have about the Euler characteristic can often be generalized to a theorem about the Lefschetz number. And so we, with Matt Wright, we generalized this Euler characteristic, or the Hadwiger's theorem to a Lefschetz number. So the dimension 0 thing of this type is the Lefschetz number, and then there are also like higher dimensional kind of, we call them Lefschetz volumes, which are like the intrinsic volumes, but they have some kind of Lefschetz information mixed into them. They're not purely topological, they're geometric. This is just a preprint. We were both kind of dissatisfied with how this turned out, and we never published it. If any of you are interested in fixing it for us, let me know. Okay, here, that was number one. Here's number two. This actually is, Kate Ponto mentioned this theorem yesterday. This is by Watts in 1961. So this says, take, again, any homeomorphism invariant which satisfies this property. This is like a cofibration property. So in this case, X and A are, well, X is the whole complex, and A is a subcomplex. And any invariant which satisfies this property, then that function must be a constant multiple of the Euler characteristic. So if you additionally say that something like epsilon of a single point is 1, then it must be the Euler characteristic. All right, this is the theorem of Watts. And this was generalized by Arkowitz and Bob in 2004 to the Lefschetz number. So there's a similar characterization. You can write a kind of a cofibration property that the Lefschetz number has, and the Lefschetz number is the only invariant which has that cofibration property plus a homotopy invariance. And then the same thing. Oh, I'm missing a thing here. I don't know why, but so the next thing I was going to say is this was also generalized to the Rademeister trace and an equivariant Lefschetz number by Dasselberg and Julia Weber.
Wait,
yeah.
So this is a property that L of f squared doesn't satisfy? Because like what I would guess is if it satisfies those properties, it's some combination of like L of f to the k.
Okay. Anyway, the third one. Let's pretend we didn't hear any of that. The third one, this is an obscure one that I found out. I looked into all of these because I was thinking of doing it like some kind of undergraduate research project about these different theorems about the Euler characteristic, which I never did that project, but I learned about. So this is a theorem by CTC Wall, 1966. So this is any integer valued subdivision invariant of a complex which satisfies this. So it is defined in some way which is a sum of coefficients times the number of simplices in each dimension. So the VI means the number of simplices in dimension I. And then it has some coefficients in front of it. Now we all know the Euler characteristic has alternating signs in front of those numbers, all right? But Wall considers any possible sum of the number of simplices. If it is a subdivision invariant, then it must be the Euler characteristic, or a constant multiple times the Euler characteristic. So what it says basically is if you add up the simplices with those AI's in front, they must be -1 to the power I. There's no other way to add together this sum with the minus ones is the only subdivision invariant way to add up the number of simplices. You can't do it any other way and get a well-defined thing. I think that's kind of interesting. This seems, at least as far as I can tell, is kind of a lost theorem. If you look this up on math reviews, there's only been 2 references to this paper ever, and they're both after 2010. So it seems like maybe nobody cared about this in the 60s when it came out, but I think it's a great theorem. Something else that's really interesting in this paper that I had never heard of this before. Wall also discovered what I would call hidden invariance. He didn't call it this, but that's what I'm going to call it. Sorry, something's wrong with the. Maybe something's wrong with the file. Sorry, can you give me a moment here? They are hidden. They're hidden, yeah. The hidden invariance. Maybe there's a reason nobody cites this paper. Okay, so what Wall demonstrated. Thank you for your help, Carl. Yep. You're going to miss this beautiful formula. There's a condition. If x is what he calls good in dimension r, this is his actual word, good in dimension r, it means basically like x is like a manifold in dimension r. So this is satisfied by all manifolds. This is automatic. Then this summation, remember v, like vi means the number of simplices in dimension I. So this strange way of adding things up, here r is less than n, and n is the dimension of the complex. This sum is actually invariant under subdivisions. If you do this for each r, that the complex is good, then this is also invariant under subdivisions. And this is not the Euler characteristic. This here is the binomial coefficient. How come nobody ever talks about this then? This is also an invariant. Anybody want to guess? The reason I assume I never heard of it, this is always 0. So, yeah. It's strange. It took me a while to understand what the theorem was trying to say. But so Watts proved that he classified all possible subdivision invariants, even the ones which are always 0. And these ones are always 0. There's also the Euler characteristic, and there's no others, right? So anything which is a subdivision invariant, when you actually add it up, it will add up to the Euler characteristic. It might also include some of those 0 parts, but it will add up to the Euler characteristic. So this is like a hidden kind of Euler characteristic, but it's always 0. So these things which add up to 0, they exist in all dimensions for manifolds. If it's not a manifold, then it may not exist in some dimensions, or it might not exist in any. All right. And that theorem, as far as I know, has never been generalized to the Lefschetz number or other kinds of fixed point invariants, which I think might be interesting. You know, for example, we know that this sum here, the definition of the Lefschetz number, this is homotopy invariant. A similar theorem would prove that that minus 1 to the I is necessary as the coefficients, that there is no other way that you could choose the coefficients to make a reasonable definition of something. So is this the only possible homotopy invariant sum of the traces? I think it must be, although I have never seen a proof of this. Does it have to be a trace right there? Could you replace the trace by some other kind of thing and still get a homotopy invariant? Probably not, but this is a kind of generalization that I imagine. And similarly, are there kind of hidden Lefschetz number-like things which happen to always equal 0, but are still well-defined kind of homotopy invariants? Interesting. And you could ask the same questions for the Rademacher trace, which also has a definition as an alternating sum of traces of something. Is that the only way that you could do it? I assume it is, but I haven't seen such a theorem. Something to work on if you're interested. Okay, one more. I said there were 4 of them. The last one has kind of a local flavor, which none of these ones before have. This is by Levitz, who I don't otherwise know, in 1992. And the title kind of tells it all here. This is the title of the paper. The Euler characteristic is the unique, locally determined numerical homotopy invariant of finite composites. So the property that Levitz is going to give here is just the fact that the Euler characteristic can be computed locally. And you can do this by just counting the number of simplices that touch each vertex. And you'll be double counting a lot of them, but you can compensate by dividing everything by n or something like that at the end. So this is the statement of the theorem. Let epsilon be any real valued invariant that is defined by some formula where you add something you add up something around each vertex. And the something depends only on the star of that vertex, so this local information. But that D there can be any function. There's no regularity assumed on D at all. It's not continuous or anything, all right? D is any real valued function. Anything which can be computed just by looking near all the vertices, it must add up to the Euler characteristic, or a constant multiple of the Euler characteristic, it must be. So this is like a local kind of theorem. And this also has not, I have not seen directly this be generalized to the Lefschetz number. Although, the kind of local flavor is what I'm going to be talking about. This is a sign from some restaurant somewhere. I said this has a local flavor. The fundamental property of the Euler characteristic that Levitz is talking about is that it can be computed as a sum of local calculations. And this is the most convenient for doing axioms for the fixed point index, at least in my experience. The fixed point index is also locally computable, so it might be possible to do some kind of copy of Levitz theorem to the fixed point index. That per se has not really been done, but this is the one that I'm going to talk most about is a theorem by Furi, Pera, and Spadini from 2004. This is a uniqueness theorem for the fixed point index, which is explicitly based on the fact that it is a localizable invariant. So this is what I'm going to focus on. This Furi, Pera, Spadini I'm going to call the FPS theorem. So I'm going to write ind of fu, that's the index of the function f on the subset u. The fixed point index, I said fixed point set, that should say fixed point index of f on some open subset u. This is only defined when the fixed point set is compact inside u. We all know the definition of the index requires this in order for it to work. So that's an assumption. And the homotopies that I talk about, there's also a compactness assumption that the homotopies need to satisfy, which I'm not going to talk about more than that. So the theorem that's in that paper is that the local fixed point index is the only real valued function on manifolds which satisfies these three properties. There's the homotopy property. If f and g are homotopic, then the index of f on a subset is the same as the index of g on that subset. There's this additivity property. So this says that if you can break the set U into a disjoint union, and that disjoint union contains all the fixed points that were originally in the subset U, then the index on the whole set, the big set U, is the sum of the index on the two parts, the A and the B. That's the additivity property. And then there's this normalization which just makes it so that you actually get the index rather than some constant multiple of the index. So we declare that the index of a constant function on the whole space equals 1. That's the normalization. All right. The local flavor of this is kind of hidden inside the additivity axiom. The additivity axiom in this one carries a lot. So this little assumption right here, the fixed points of U are contained in A union B. That allows you, if you use some giant set, but it only has like 2 fixed points in it, you can immediately shrink down the whole set to this A and B, where the A and B are anything smaller, but they just have to contain the fixed point sets. So this allows you to ignore basically all the parts of U which don't have any fixed points by that additivity property. All right. This is the FPS theorem. This has been generalized in many ways. So to the coincidence index, a very similar result. It's also been done for the Reidemeister trace in fixed point theory and coincidence theory also. It's been done even on non-orientable spaces, like something like the semi-index, although it's not exactly the semi-index. Semi-index doesn't have a nice additivity property, but Dasselberg and I did something with that a few years ago. All right. This is always about manifolds. You might have noticed that the FPS theorem requires manifolds, and actually, I'm not sure if it's even true if they're not manifolds, because strange things can happen on a complex with a wedge point. The index can change in unpredictable ways, or weird things can happen with the index. So yeah, stay tuned for Mike's talk about that. You going to define the index?
No.
All right. My man. All right. Here's a fun application of the Fourier-Pera-Spadini theorem. This is an averaging formula for the fixed point index. So if we have a finite regular covering, and say the covering group is some group K, then this is a true fact about the fixed point index. The index of a set sort of downstairs can be computed as the average of the indices of all the coverings. This is something that actually this formula is not terribly interesting for the fixed point index by itself, because in practice, if U contains a single fixed point, then all the coverings, only one of them is non-zero, so the average is not so interesting. But anyway, this averaging formula, if it's true, immediately gives you averaging formulas for the Lefschetz number, and you can do the same thing for coincidence theory. It's not so hard to prove this averaging formula by hand, like using, you probably wouldn't use the definition of the index, but maybe just the fact that the index is a homeomorphism invariant, and so locally the covering, whatever. But we can also demonstrate this very easily using the axioms, and I thought I'd just do this as a simple kind of warm-up example. Let's make this definition. So that sum on the right-hand side of the formula, it equals something, so I'm going to call that this iota of f and u is defined to be the average, all right? And we just have to note that this function, the average, is homotopy invariant because the index on the right side is homotopy invariant. So that is homotopy invariant. It does also satisfy the additivity property if I break the set U into two disjoint subsets, because inside the index on the right side, it satisfies additivity property. And it also has the normalization property. The index of a constant is 1. This you have to do a little bit of work, but not much. Inside the sum, if I use the constant, they will all be 1 inside the sum, and they add up to the number of elements of k, and then I'm dividing by the number of elements of k, so I get 1 on the right side. Okay? So because this average does satisfy the 3 axioms in the Fourier-Perot-Spadini theorem, that means it must be the index of f, because the index is the unique function which satisfies the property. So then I've proved that the averaging formula is true. All right? It's pretty great. You know, you can use the axioms to prove any kind of formula of this type. Like if you have some formula that you want to prove about the index that says the local index is equal to some kind of other, maybe a sum or some other formula in terms of other indices, you can use the axioms to prove this, because probably whatever you write on the other side is a homotopy invariant, and it is additive and all of those other things. So I would say the moral of the story here, any formula for the index equaling some other indices will be true by the axioms, as long as it's true. So it has to actually be true. You can't just make up whatever you want. But probably if your formula actually is true, you can prove it pretty easily using the axioms. All right? This is my slogan for the day. You can tweet this. It's short. Yeah. All right. Okay. Now, in general, the Nielsen number does not have a nice averaging formula. Actually, there's a poster out here about an averaging formula. So in some cases, it does. There's a poster about an averaging formula for infrasolved manifolds, and this is one of the recurring topics every time we come together. We see some averaging formula which is proved for spaces which have longer names. So this is the latest infrasolved manifolds. For the Nielsen number, so if you have some restrictions on the spaces, you can prove this averaging formula. But actually, Liu and Zhao in 2015 proved an averaging formula for the Rademacher trace, which doesn't require any assumptions on the space. It doesn't have to be infra anything. You can average the Rademacher trace. So this is another example, which Kate talked a lot about this point of view. But this is another case when the Rademacher trace is more well-behaved than the Nielsen number, because somehow it works better when you try to make formulas like that. All right. I thought I'd show you just the averaging formula that Zhao came up with, and Liu and Zhao. I don't know Liu. So if I have the fundamental group of X, I'll call that G. So the Rademacher trace is an element of the abelian group generated by G mod the twisted conjugacy relation. And if I have a finite regular covering, and this time I'm going to say the covering group is H, which must be a subgroup of G because G is the universal covering group. And then there's this averaging formula. So it looks like the one that I wrote before for the index. But this time we're dividing by this, the index of the group. And the summation is over the quotient. And then I have this extra little rho beta. That's because if you compute all these Rademacher traces of the lifts, the answer lives in a slightly different group than the group that the Rademacher trace lives in. So you have to push them all into the big group. But it all works out just fine. All right. So in the same way, this is not the way that that Liu and Zhao did it in their paper, but you can prove this theorem, this averaging formula using axioms for the Rademeister trace, just in the same way that I just did with the fixed point index. All right. And we actually did this. J.B. Lee and I used axioms to prove a similar Rademeister trace averaging formula for coincidence theory. Actually, we did two separate proofs. He kind of wrote a proof by hand, and then I wrote a proof using axioms, and we couldn't decide which one to use in the paper, so they're both in the paper. So you get 2 for 1. All right. This is still unclear for non-orientable manifolds. It's not clear how you can do some parts of the averaging. I don't know if it's true or if you can even say anything about it. So let's get to the Nvalued Index. Just at the end here, the actual topic of my talk is the Nvalued Index. So if I take an Nvalued map called F, Shermer defined the local index of an Nvalued map in the following way. If you have an isolated fixed point of your function, remember that means some point x where x is an element of f of x. And you, if it's isolated, then you just take a small neighborhood around that point, which doesn't include any other ones, and make that neighborhood simply connected. Then on U, because U is simply connected by the splitting theorem that John mentioned, F will split as n single-valued maps. And only one of those single-valued maps has a fixed point at that point that you're talking about because the values have to all be different, so only one of them can equal x. And then you define the n-valued fixed point index on U is equal to the normal fixed point index of that one which has the fixed point. So you split the map, then only one of those split functions has a fixed point, and that's what you use as the index for the n-valued map. So I'm going to write this ind n, just to remind you, I'm talking about this is the n-valued index, and this is the ordinary index of a single-valued map. All right? So this is the definition of the n-valued index. I didn't really tell you the definition because I didn't tell you. It's defined in terms of the single-valued index, which nobody tells the definition. All right? So this is how Shermer defined the n-valued index. Here's an easy theorem, uniqueness of the n-valued index. The n-valued index is the unique real-valued function satisfying these properties. Homotopy, additivity, just like in the FPS version of this theorem. And then this third one is what I call the splitting property. And it just says if the function splits on your set and it only has one fixed point, then the multi-valued index of that function is equal to the classical index of whichever of the split maps you did. This is not terribly interesting, although it is true that the n-valued index is the unique function that satisfies these properties. Shermer actually proved each of these three properties in her original papers about the n-valued maps. And so the index does satisfy these properties. It's also the only one, and you should feel like I'm not saying too much here because this is kind of already the definition of the n-valued fixed point index. You consider, you make all the fixed points finite, or you make the fixed point set finite, and then you just shrink all your neighborhoods down and define it in terms of that splitting. So this is more or less the definition, so this is not a surprise theorem. The splitting property used as an axiom is a very strong property. You know, ordinarily we'd have just a normalization in that position, which is much weaker. This looks like I'm really saying something pretty sophisticated. But actually, this, even with that weird splitting axiom, that uniqueness theorem is enough to prove an averaging formula in exactly the same way as I said before. So here's an n-valued averaging formula for the n-valued, or the fixed point index of an n-valued function. It's exactly the same. And you prove it by those three properties again. Rather than the normalization property, it's easy to see that what you see on the right-hand side is it does satisfy the splitting property. So that's easy enough. The proof is just like what I said before. You can also use axioms to prove something like a product formula. I'm gonna kind of give you a fake version of the proof, but this is the product of the index. This is a formula that's true of the fixed point index also. Here's kind of a fake proof. You can divide things around, move the formula around like this, and like I said, like I did before about when I talked about proving the averaging formula, I define something to equal that quotient there, and then you can show that the right side there, it satisfies the homotopy property and the additivity property and the splitting property. And so this iota, which satisfies the three axioms, it must actually be the index of f, and so you get this formula back again. That assumes that this denominator over there is not 0. You have to talk about that specifically separately. But this is a basic idea. All right. Can we talk just briefly about the strong splitting property? That's really too strong to be, as an axiom, I would like it to be quite a bit weaker. Instead of that splitting property, it would be nice to have a more ordinary-looking normalization property. In the single-valued case, the normalization property is this. The index of a constant taken over the whole space is 1. In the n-valued case, you can still talk about a constant. A constant function in an n-valued case is not a choice of a single point. It's a choice of n different points. So actually, in the n-valued case, this index taken over the whole space, it ought to be n, not 1, because a constant function has n different fixed points of it. So you can't exactly say the index of a constant should equal 1. It shouldn't. It should equal n. But actually, if you make it equal n, then you don't necessarily get all the values that you would want to get. If you're using that as a normalization, then the only possible values you could get would be like multiples of n, which is not how the index is actually supposed to work. So the modification is this. So as a normalization axiom, the property that we use is that the index of a constant function is 1 when the set U contains one of the values of the constant. So that's what I'm going to use for the normalization. It's not a complicated idea. All right, anyway, this is the final theorem. When X is a manifold,
again, I'm not sure if
then
this
the
is
index
even true
is
if X
unique
isn't a
with respect to
manifold,
these three properties.
because,
And you can
like
see
I
that
said,
that weird things can happen when it's not a manifold if you're looking at the local index. So that's an interesting thing to think about. All right. And I think that's it. You can look at this talk again if you want to see at my website. Thanks.
Do we have any questions for the speaker? I think I see Darcy.
Just one comment.
Yeah.
For coincidence, I think it
So it's the map is not n points but n components each time.
No,
It could be n
points
points.
is a
Yeah,
particular
yeah,
case.
right.
Yes, even more general case of n acyclic paracyclic components.
Do we have any other questions? Yes, no.
Yeah, I didn't think about that for the Nvalued index, but in the paper with Dassieberg we talked about if you assume the value is not necessarily a number but in some abelian group, then you can show that if you assume that so you have a normalization that says the index of a constant is a. It may not be 1. It's just something. Then all the values of the index must be multiples of a, and basically the values of the index will be a subgroup of whatever your abelian group is that's isomorphic to the integers anyway. Right? So even if you assume that they're, like, I don't know if anybody noticed, some of these theorems were stated in terms of any integer valued function, and some said any real valued function. It doesn't matter if whatever you assume the function, whatever group its values are in, they will always end up being integers anyways, or integer multiples of whatever you use in the normalization. Yeah. Oh, well, so it could also be some kind of if your group of values, if you normalize to an element which has a finite order, then it will be like z mod n, or z if it's infinite order.
All right, do we have any other questions? All right, then let's thank the speaker.